Swayam Prabha. Digital India. Educated India.
So recall from yesterday we were trying to design FPT algorithms for problems, and the goal is the same today. So yesterday we saw kernelization as a way to design FPT algorithms, where starting from an instance we reduced it to an equivalent instance whose size was bounded in the size of the parameter, and hence and we could do that in polynomial time. So we'd spend polynomial time from coming to an instance whose size is small as in bounded in the size of the parameter, and then we know we can brute force for most of the problems and solve that instance, right? And the brute force time will be it will be some function, probably exponential, but it's exponential in the size of the input, and because the size of the input is only some function of k, whatever time we spend to solve the reduced instance, it will be some function of k, right? So this is how we design FPT algorithms. So today we are now we can forget about kernelization, in the sense that today we are going to see a different technique that is widely used to design FPT algorithms. And again, you have already seen that technique in terms of in the context of exact exponential algorithms. So remember, Venkatesh taught you exact exponential algorithms, right? So he taught you, for example, there also he taught you vertex cover, and he gave you some 1.618 to the power n algorithm for vertex cover. What we're going to do is, surprisingly, we're going to use, let me say, almost, or at least at the look of it, the same algorithm that he taught you to get a 1.618 to the power n algorithm, but we'll just view that algorithm a bit differently, differently, as in we don't have to think a lot. At the look of it, we'll just look at it and we'll observe that the same algorithm, was giving you a running time of 1.618 to the power n into maybe some polynomial in n running time for the problem vertex cover, right? So we'll see how we can use the same ideas to get 1.618 to the power k algorithm into polynomial in n for vertex cover. Note that this algorithm, 1.618 to the power n algorithm for vertex cover, using this algorithm you were trying to solve the optimum vertex cover. You were trying to find the minimum vertex cover in a graph. And our goal, we are working with decision problems, right? So our goal is to find, we are given an integer k, and our goal is to find, is there a vertex cover of size at most k? That's the only difference, and with that we'll get an algorithm whose running time is 1.618 to the power k. And note that, of course, k could be as bad, k could be as bad as n. So if suppose you're asking, is there a vertex cover of size at most k, at most n, our algorithm will run in time 1.618 to the power n, of course, right? So as I said, parameterized algorithms, in the worst case, they might run as bad as any exponential time algorithm, but why we design it is because we know that if k is small, this will give you better. For example, the first algorithm, if I tell you that, okay, I'm only interested in finding out whether the graph has a vertex cover of size at most 5 or not, then you don't know whether the first algorithm will give you a good running time or not. But if you look at the second algorithm, you know definitely it will give you a good running time when k is equal to 5, for example, right? So yes, in worst case, it might be as bad as the exact exponential algorithm, but we know that if k is not very large, then this will give you good running time. So that's the goal. So before jumping into designing 1.618 to the power k algorithm, let us just try to design a 2 power k into poly n algorithm for vertex cover, okay? And then we'll try to improve it to 1.618 to the power k. And to do so, first of all, can you give me a 2 power n into poly n time algorithm for vertex cover? Of course, you can look at all possible subsets of the graph and check if that's a vertex cover. That will give you a 2 power n time algorithm. But can you give me a branching algorithm? You've already seen branching in the term of exact exponential algorithms. So can you give me a branching algorithm that takes 2 power n time for vertex cover? Or do you remember how this 1.618 to the power n algorithm worked for vertex cover? What did you do there? Yes, exactly. So let's go with that. So you're given a graph G, and you just arbitrarily pick some vertex u in G. You know that any vertex cover any vertex cover either takes u into it, so u belongs to the solution, or u does not belong to the solution. But you know, if u does not belong to the solution, then all the neighbors of u should belong to the solution, right? Right? So if you start with a graph on n vertices, these are the two possibilities, and if u belongs to the solution, you can reduce the problem of finding vertex cover on the graph g minus u. And if nu belongs to the vertex cover, then you can reduce the problem of finding vertex cover on graph g minus nu, right? And then now you do the same thing recursively. So branching algorithm is a recursive algorithm. So you know that to find a minimum vertex cover of G, it's enough to find a minimum vertex cover of G minus U and G minus NU, because the minimum vertex cover of G will be min of minimum vertex cover of G minus U and minimum vertex cover of G minus NU, right? I mean, this is what you saw in the branching algorithm that was taught you. And so basically, how does the algorithm work? The algorithm computes a minimum vertex cover for G minus U, the algorithm computes a minimum vertex cover for G minus NU, compares the two values, whichever is smaller, it returns that as an output for the minimum vertex cover for G, right? And how does it compute the minimum vertex cover of G minus U and G minus NU? Recursively. It again branches on some vertex in G minus U and do the same thing, and branches on some vertex in G minus NU and do the same thing, right? And how did you measure the running time of this algorithm? So it's a recursive algorithm, right? So you write a recurrence to measure the running time. So you say, let us say that, what does Tn denote? Yeah, I get that Tn. But first of all, you have to tell me, what does Tn denote? Like, what does Tn represent? This is the recurrence that we wrote. See, normally we say that, like in this case, what is Tn? Tn is the time taken to compute the vertex cover of on an n vertex graph. So even before writing this recurrence, we should first tell what does Tn denote. So let Tn denote the running time to compute a minimum vertex cover on an n vertex graph, right? And we know, and now we write this recurrence. So what do we want to write? We want to compute what is the running time to compute a vertex cover on an n vertex graph. And from our branching algorithm, we know that to compute a vertex cover on an n vertex graph, it's enough to compute a vertex cover on, for example, in that case, G minus U, or in other words, a graph on n minus 1 vertices and a graph on n minus neighborhood of U, but neighborhood of U is at least 1, right? So if of course, if neighborhood of U is not at least 1, then what can we say? It's an isolated vertex. So even before doing this branching algorithm, we'll have a reduction rule that would delete all isolated vertices, and we saw yesterday that reduction rule is safe. So you can always do this pre-processing. In fact, whenever you design algorithms, if you can do pre-processing, you just do it, because that only helps to get better algorithms. So even before this branching algorithm, we'll have this reduction rule that we had yesterday, that says that, okay, if you have a vertex of degree 0, delete it. In fact, if you want, if that helps, you can even, like, you could have even applied the second reduction rule that we had yesterday, because that was also safe for designing vertex cover algorithms. It's just that will not give us anything better for this branching algorithm, so we don't apply it. All I'm trying to say is, if you have seen a reduction rule for a problem, you can always apply that to whenever you're trying to get an algorithm for that problem, if that turns in favor of you. But anyway, what we know is that the neighborhood of U is at least 1, because we have applied the reduction rule, that deletes degree 0 vertices. So we know this recurrence is Tn is at most Tn minus 1 plus Tn minus 1 at least, because the neighborhood of U will be at least 1, right? So this is the recurrence that you get, and when you solve this recurrence, what do you get? Like, what does this recurrence solve to? What will be the value of Tn now? Okay, I have to tell a base case first of all, sorry. So this is the recurrence. What is the base case? So suppose In the base case, you have a graph on one vertex. What should be the running time to compute a vertex cover on a graph on one vertex? Yeah, so you can actually delete it. So it just takes some constant time, right? So I'm just writing T1. And now you have to solve this recurrence. What does Tn solve to? Anyone? This is simple. I was told that you all knew how to get this, how to solve this 1.618 power n recurrence that you just saw. So this is much simpler. So again, you can write Tn minus 1 as, what is Tn minus 1? You can write it as Tn minus 2 plus Tn minus 2, right? So it is Tn minus 2, okay, wait. In fact, you can write for ease, you can write this as 2 into Tn minus 1. And now you just open this. This is 2 into Tn minus 1. And you know Tn minus 1 is nothing but 2 into n minus 2. So this is basically 2 power 2 into Tn minus 2. And you keep on doing this. Eventually you will get 2 power n into T1. And T1 is 1. So you will solve it to 2 power n. Okay. Yeah, so this is how you get a 2 power n algorithm for vertex cover. Okay. So now let us use the same idea to get a 2 power k algorithm for vertex cover. 2 power k into some poly n algorithm for vertex cover. Okay. And again, we'll do the same thing. Note that because it's a decision problem, so with G we are also given an integer k. And the goal is to find a vertex cover of size at most k in G. Okay. Again, we do the same thing. We pick a vertex, like we pick an arbitrary vertex u in the graph. We know it either goes to the solution or it does not go to the solution, right? If it does not go to the solution, we know all its neighbors should go to the solution. What can we do if u goes to the solution? Yeah, so just delete u from G and you have to decrease k by 1 because you are forcing u to go to the solution. So now you have to look for a vertex cover of size k minus 1. Similarly, in this branch, what do you have? Right? And you keep on doing this. So when do you stop here? So for example, in this 2 power n algorithm, you stopped when the graph had only one vertex. K power cardinality of n. Okay. So the instance here is G minus nu, comma k minus nu. Yeah, I'll not write the last bracket, otherwise I'll go out of space. Anyway, and then again you branch on this, right, and keep on doing this. So what I was saying is, to get a 2 power n algorithm, when did we stop? When the graph had only one vertex, because every time we were deleting some vertex from the graph, and we stop when the graph has only one vertex. In this case, again, we can keep on doing the same thing. Exactly. So do we really need to wait till the graph has only one vertex? Because note that in each step, our k is decreasing. So suppose we keep on doing this and we have reached a state where we have some graph G prime and k becomes 0. Then do I still need to find a vertex and branch on it? No, because here I know in this graph I'm looking for a vertex cover of size 0, and I can see in polynomial time if this graph has a vertex cover of size 0. How can I check that? How will G prime look like if it has a vertex cover of size 0? Exactly. So I just have to check if G prime is an independent set. It forms an independent set, right? So I don't have to go till n steps. I can stop after k steps. So what do you think? How much running time will this algorithm take? At least think. Like we'll see it formally, but what does it look like? Okay. So with a branching algorithm, you can always associate a branching tree. So what is a branching tree, for example? So branching tree is, for example, this is the first node. So you start with gk. This is the first node. Then you branch into two instances. So look at that thing as a tree. So this is the first node of the tree. These are the edges of the tree. Then this is the second node or vertex of the tree. This is the vertex, and then again you branch on instances. You see a tree-like thing here? This is called the branching tree, corresponding to a branching algorithm. Okay, and if you notice, running time of any branching algorithm is proportional to the number of nodes in this branching tree. Right? So basically, you can look at the running time of a branching tree as the number of nodes that you have in this branching tree into the time taken at each node. For example, look at this 2 power n algorithm. How many nodes will be there in this branching tree corresponding to 2 power n algorithm? So you start with a graph on n vertices. Then that's the first node of the branching tree. You make 2 new nodes corresponding to each branch. Then again you keep on doing this. You keep on doing this till how many layers? N layers, right? So you have started with a graph on n vertices. At every vertex you have 2, for every node in the branching tree you have 2 children, right? So this branching tree basically looks like a binary tree, right? And how many nodes are there in the binary tree? Or okay, even before that, what's the depth of this binary tree? N, right? Because you start with an n vertex graph. The last graph, you stop when you have a graph with 1 vertex. So the number of nodes in this binary tree is 2 power n, right? And okay, so similarly, how many nodes are there in the branching tree that we just wrote? This one, like this one, this branching tree, how many nodes are there here? Exactly, there are 2 per k. So basically, you could write a recurrence like this. So the number of branching nodes in this tree is 2 per k. So another way of looking at running times of branching algorithms is just compute the total number of nodes in a branching tree and see how much time are you spending at each node of the branching tree. Time taken by this branching algorithm is at most number of nodes in this branching tree into time taken at each node. When I say time taken at each node, meaning each node corresponds to an instance, right? So time taken, like when I'm at that node, how much time will I take? Yeah. So for example, suppose I'm at a node corresponding to the first instance, gk. How much time will I take there? Like what am I supposed to do there? I'm supposed to find a vertex in the graph, and yeah, I just want to check if there is a vertex in the graph which have some edge incident on it. Okay. Or in other, like that's all that I have to do. So how much time am I spending at the node gk? Constant, or see, I have to check if there is a vertex of degree at least 1. Omega of what are you saying? V. What is V? V is a vertex. In linear time, you mean. Let us say G has n vertices. So you'll spend some n time, right? So you are just checking, is there a vertex which has degree at least 1? So if there is no such vertex, you know the graph is an independent set and you can just say yes for this. If you have a vertex of degree at least 1, then you are branching, right? So now again, at every node, like look at the node corresponding to g minus u comma n k minus 1. Again, you are checking if there is a vertex in this graph which has degree at least 1, you will branch. Suppose you don't get a vertex of degree 1, you don't have to go to, you don't have to proceed further in the branch then. Like we said that in a branching tree we have to go till we get this instance where the k becomes 0, right? Suppose we are at a node, and at this node we realize that there is no vertex that has degree at least 1. So how are we going to branch on this node? We can't, because for branching we need a vertex with degree at least 1, right? Only then will I get this that k drops to 1 in this branch, and I'll either pick that vertex or I have to pick its neighbors. So if I pick this vertex, k drops by 1 in one of its children nodes, and if I don't pick it, I have to pick its neighbors, and because it has at least 1 neighbor, then k drops to 1 in the other children node. But if I don't have any vertex, then we know then the graph is an independent set. So if I'm unable to find a vertex of degree at least 1 here, I know the graph is an independent set here. Then what can I do? Then I know this is a yes instance. So why were we branching? We were eventually branching to find, like we wanted to know if it's a yes instance or no, and we were trying to do it recursively. But now I don't have to branch further for this instance because I know it's a yes instance, so I can just stop here, right? So if at any point you are not able to find a vertex to branch on, that means you are not able to find a vertex of degree at least 1, you know the graph is an independent set, and hence you can just say yes and stop there. Yeah, so the point I was trying to make is this, that the time taken by any branching algorithm is the number of nodes in the branching tree into the time taken at each node. So the time taken at each node here now is some polynomial. As you said, it's linear in the number of vertices. Let me just say polynomial. Like the number of nodes, as you can all see, we'll write that formally also, but as you can all see, the number of nodes in this branching tree is 2 per k. So can I say that the total time taken by this branching tree is 2 per k into poly n? Because at any point you start with a node, you spend polynomial time at that node, then you branch into other nodes. At each node you're spending polynomial time, and the total number of nodes that you'll be looking at is only 2 per k, right? So yeah, this is one way in which we can analyze the running time of the branching algorithm. And the important thing to note here is, see, in this branching tree it was easy to see that the number of nodes in this branching tree is some 2 per k, okay? But for example, we'll just slightly improve this algorithm to get a 1.618 per k algorithm, and when we design a branching tree, it might not always be easy to see how many leaves, how many nodes are there in the branching tree. So to compute the number of nodes in the branching tree, what we do is we write a recurrence, okay? So basically, what is a branching algorithm? We design a branching algorithm, we start with an instance and we branch on that instance, okay? The correctness of the branching algorithm follows from the fact that when we have an instance, when we branch in such a way that we say that, okay, either this, like if the original instance was a yes instance, then one of the instances on which I branch have to be a yes instance. Like for example here, if gk was a yes instance, then either g minus u comma k minus 1 is a yes instance, or g minus n of u minus k comma k minus n of u is a yes instance, right? If both are no, then I know there is no vertex cover in G of size k, because both can't be no. This is again the same kind of argument that we did in the first class yesterday. So the correctness follows from that, and then the running time is given by this expression. One more small thing, I think we just made a little mistake. So look at this branching tree, look at any branching tree, either this 2 per n algorithm or the 2 per k algorithm. We said that the number of nodes here is 2 per k. Is it true? Are there really 2 per k nodes? I'll just draw. So let's forget about everything. So what I'm asking is a very graph theoretic question. You have a graph, so you have a tree, this, every time it's like, it's a binary, basically we have a binary tree whose depth is k, right? This is how the branching, okay, this is how the, just a second, this is how the branching tree of our algorithm looks like. And we said that, and we were interested in bounding the number of nodes in this. So how many nodes are there in such a tree? So what is it? It's a binary tree of depth k. How many nodes are there in such a tree? 2 per k. Sorry? Yeah, so it's not 2 per k, right? So this tree has 2 per k leaves. Yeah, so it's 1 plus 2 plus 2 per 2 plus so on till, right? Okay, this. Another way of getting this bound could be, if I prove to you, suppose I tell you that the number of leaves in this tree is 2 per k, then can you tell me how many, if I suppose just tell you this, that the number of leaves in this tree is 2 per k, then can you bound the number of nodes in this tree? So do you know of any relation between the number of leaves in a tree and, so let me call a vertex an internal vertex of the tree if it's not a leaf, okay? So do you know of any relation between the number of leaves in a tree and the number of internal nodes? It is less than that. Yeah, but there is a slight catch, as in, so for example, I could have a tree like this. How many leaves are there in this tree? 4. How many internal nodes are there? A lot. I can draw as many as I want to. It's not a function of the number of leaves, right? Exactly. Complete, or in other words, look at the internal nodes that have at least 2 children. Okay, so basically look at all the internal nodes. So internal nodes again are the nodes that have no leaves, that are not leaves. So look at all the internal nodes that have at least 2 children. The number of in any tree, the number of such nodes is actually equal to, so the number of such vertices is equal to the number of leaves in the tree minus 1. This is very easy. If you have not seen it, maybe you should just try to prove this. Okay, and basically now if I tell you that the number of leaves in the tree is 2 par k, and we know our branching tree is a complete binary tree, so every internal vertex in our binary tree will have at least 2 children, right? So the total number of internal vertices in our branching tree will be 2 par k minus 1, right? So this gives that the total number of nodes in our branching tree is 2 par k plus 2 par k minus 1, which is what he said, 2 par k plus 1 minus 1. So this is another way of looking at it, right? So, and why I wrote this is again because this was like the branching algorithm that we saw was a very simple branching algorithm where we got a branching tree that was a full binary tree, right? So as we'll see in other examples, it will be easier. No, it's not really easier, but mostly what we try to do is we try to bound the number of leaves in the branching tree that we get, and then using that bound, using this relation, we are able to bound the internal nodes of the binary tree and hence the total number of vertices in the binary tree. Okay, and why are we doing all this? Because we want to bound the number of total number of vertices in the branching tree to get an upper bound on the running time of the branching algorithm. Okay, so this was some tree stuff. So coming back to the branching algorithm, so we designed a 2 par k algorithm here, right? So again, this is in the same spirit as the 2 par n algorithm that we saw, right? So, but you have seen a 1.618 power n algorithm for vertex cover, right? How was it different from this 2 par n algorithm? So what gave you 1.618 par n? Sorry? See, okay, let's see what was, basically we had this recurrence for this, and this recurrence was solving to 2 par n, right? And why were we getting this recurrence? So again, let me just expand it again. Can we, sorry? Why would you want to do that? Why is it correct to do that? Because you will be, yes, of course we can. No, wait, think about it. Why is it not correct? So so we are in this algorithm now. You are saying in this algorithm, let us delete u with the neighbors of u. Okay, wait, sorry. So yeah, actually I think, yeah, you can. So basically in this branch, you know that u is not in the solution and you're picking all the neighbors of u in the solution. So once you pick that, the number of vertices will actually, and then you would basically apply this isolated vertex rule. So basically in this instance, you would have decreased the size of this instance by at least 2. The neighborhood of you can actually delete the neighborhood of closed neighborhood of u. Right, yeah. So basically, in this case, then you can directly get a, in this recurrence, you'll get n minus 1 and n minus 2 here. And this solves to, this is that golden ratio thing, right? This solves to 1.618 power n. Let's see if we can try to do the same thing here. Okay, can we do the same thing here? Okay, so here, so now in this case, if u goes to the solution, fine. If u does not go to the solution, we pick all the neighbors of u. Of course, from the graph, we can delete n of u, like n of u and u both, right? But note that we can't change k. K only goes to k minus n of u, right? Yeah, and we are trying to bound the size of this branching tree as a function of k now, right? We are not trying to bound the size of this branching tree as a function of n, right? So at least at the look of it, the way we are doing it, again, we'll keep on doing this branching until we get to an instance where k is 0, right? So it's not clear why we'll do any better than 2 power k, at least in this case, right? But again, note that if every time I was able to find a vertex which had at least 2 neighbors, suppose, so for example, every time I'm finding a vertex, I was finding a vertex of degree at least 1 and branching on it, right? Suppose instead of finding a vertex of degree at least 1, I find a vertex of degree at least 2 and branch on it. Then what happens? So if u goes to the solution, fine, we put u in the solution, decrease k by k minus 1. If u does not go to the solution, all the neighbors go. But what is the size of this? It will be at least 2, right? So now at least intuitively it looks like this, at least for example this branching tree, like it will not be a complete binary tree now, right? You will not have all 2 power k nodes here, because basically here, here you will have a basically in this branch in this branch at max you can have a complete binary tree with, of depth k minus 1 at max. Maybe here also when you branch, you will branch into k minus 1 and k minus 2, but at the number of nodes in this binary tree will not be more than the number of nodes in a complete binary tree of depth k minus 1 here, right? And if you look at this binary tree, again the number of nodes in this binary tree cannot be more than the number of nodes in a complete binary tree of depth k minus 2, because